Hello everyone, today we'll learn about Fourier integral. Fourier integral is a non-discrete analogy of a Fourier series. The representation of a function given on a finite interval of the real axis by a Fourier series is very important. Formula of Fourier integral is a formula for the decomposition of a non-periodic function into harmonic components whose frequencies range over a continuous set of values. Here we can see the Fourier integral of a function f of x defined on minus infinity to infinity is f of x equals to 1 by twice pi integration of f of alpha into e to the power I alpha x d alpha. Here we can see this f of alpha is Fourier transform. This f of alpha is equals to integration of f of x into e to the power minus I alpha x dx. We have discussed about Fourier transform in our last class. So find Fourier integral representation and the Fourier transform of the function f of x equals to 1, 0. Here 1 is for the 0 to this range and otherwise it will be 0. Okay. So the Fourier transform is f of alpha is equal to Fourier transform of f of x equals to integration of fx into the power minus I alpha x dx equals to integration of 0 to 2 e to the power minus I alpha x dx. Okay, we'll do the integration here as it is not elaborated here. Here we can do the integration. So this is 0 to 2. Actually, we haven't write this range. This is 0 actually. So we will write actually only 0 to 2 as other components will be 0 here. So we'll just write the non-zero components. Okay. So we'll write this 0 to 2 range here. Okay. Now we can say that this is the exponential here. So we'll integrate it. Okay. Now after integration, what will we get? We get 1 divided by I alpha 1 divided by I alpha e to the power minus 1 minus I alpha x. Okay, now we will write the upper limit and lower limit here. Okay, where just write the upper limit and lower limit, and then we will put the upper limit and lower limit as we have done the integration. Okay, now we'll put the 2 here. Okay, I alpha e to the power, now e to the power minus, we can say that I alpha. So s x equals to, we'll put 2 here. Okay, 2. Next, okay, this is the, actually you can bracket here. So for the lower limit we will do what? 1 minus 1 divided by I alpha, it will be same. But in case of exponential, in case of the power of the exponential, what will we write here? We will write 0 for x here. So actually any value multiplied by 0 will be 0. So we'll write here 0. Okay. So we can replace this e to the power, sorry. We can replace this e to the power 0 by 1. Okay, 1. So if we take common this 1 minus this, if we take common minus 1 by I alpha, what will we get? We will get minus 2I alpha. It will be same here. This power will be same, and as after taking the common, here we'll write minus 1 just. Okay, so these and these are same, so we have got our Fourier transform here. After getting the Fourier transform, we will do the Fourier integral to this equation. So just put the Fourier transform here. F of alpha is replaced by this transformed form. So now we have got this equation through replacing the f of alpha by this. Okay. So come to the application of Fourier transforms to binary value problems. In mathematics, in the field of differential equations, a binary value problem is a differential equation together with a set of additional constraints called the boundary condition. A solution to the binary value problem is a solution to the differential equation which also satisfies the boundary condition. Here we can see here, this condition is boundary condition, okay? U of x comma 0 is equals to fx. This is the boundary condition, which is a constraint to this differential equation, we can say here. So we will just first we will do this Fourier transform. We can say here we can take this. After doing this Fourier transform, we can get this. Okay. After doing Fourier transform, we have get this. So then we will just Fourier just use formula and replace this f of this f of term here. Okay. Now we can say that this f of u is equals to u bar. We can let f of u equals to u bar. Okay. Equals to, we can take u bar, just this. We just take this u bar here. Okay. Just replace it. Okay. Just f of u equals to u bar. Okay. Now we will take this u bar to the denominator here and do this and to get this formula. Then after integrating both sides, we have got log u bar equals to minus alpha square s square t plus log c. Okay, so it will not be here. Just. Okay, now we can get how we can get this log u bar from this du bar divided by u bar. We can say here that 1 divided by u bar, we can say 1 divided by u bar. This is the integration formula. We can recall this, that something integrated like this, we will get then log of u bar. Okay, so we have got this log of u bar, and this will be same here, this will be same here, just just taking the integration of it. Okay, just taking the integration of it, we will get minus alpha square s square t into t plus log c. Log c is a constant here. Okay, now we'll just replace it and just reorder it. Okay, and then we can get some, and then we get at last this u bar of s of t equals to c into e to the power minus alpha square s square into t. Okay, we can say that u bar equals to u bar of s of t. Just these two are same. We can say here, just we have put this variable here. Okay, so we have just put this variable here, and now t equals to 0 and u bar of s of t equals to c. So for a Fourier transform, we can get here this. Next, we get this equation. So we will put this t equals to 0 here. Okay, after putting t equals to 0 here, we will get this equation, which is equal to f of s. So c equals to f of s here. Then u bar of s comma t equals to f of s into e to the power minus alpha square s square t. So from the inversion theorem, we can get this. So at last, we will replace this u bar of s comma t by this f of s into e to the power minus alpha square s square t. Here we can see this. Okay. So thank you. That's all for today.